Good morning, mathematicians. So I claim I'm not bad at math. I'm just bad at reading. I misread the linear algebra problem we were working on yesterday. And that is partly why it didn't make sense. So, in honor of that fact, I've decided to title the stream "The Truth" is that I'm just bad at reading comprehension. Gotta open archive every morning. That's always our other page. So what was the problem actually supposed to be yesterday? Oh, by the way, new group cohomology video dropping today. Okay, 1 second. I gotta pour myself some coffee. Well, we can be both. I believe in a world where we can be both, but it's as of yet to be determined. Perhaps I should say I should have said, well, I'm definitely bad at reading. Maybe I don't know yet if I'm bad at math. Okay, so here's the problem from yesterday. Here's what the problem was supposed to be. I went back. I just read it wrong from chat. So if the matrix has finite order, this means actually the some finite power of the matrix is the identity. Then the matrix, not only did you make it in, but you're here right at the start, Lockheed. Then this matrix, the power of 12, must be the identity. Good morning, Matthew G. So, I used to have a stand for this, and I do still have one, and it's at the office. What I really need to do, I need to invest in some lapel mics anyways for interviewing purposes. Yeah, so this is what we're trying to prove for 2x2 matrices. And, okay, so I think this isn't going to be a nice proof. You have a whole 3-hour journey from uni to home now? Oh my god. 3 hours? Man, I would give up and become a plumber. No, you shouldn't do that, but 3 hours is wild. I can't conceive of this. I would never. So of course, if this is true, that means that this is true. So that means our characteristic polynomial has to divide this cyclotomic polynomial. But we also know that the characteristic polynomial of our matrix is supposed to be quadratic. Yeah, it's supposed to be quadratic, where the middle will be the sum of our eigenvalues, and this will be the product of our eigenvalues. So that narrows the choices, right? What are the polynomials that divide the cyclotomic polynomials? The quadratic polynomials dividing cyclotomic polynomials. There's not a lot of them. Let's look it up. When I put my mic down, is it really annoying? Is it an obnoxious sound? I don't know. cyclotomic polynomial. These are the isn't the cyclotomic polynomial, strictly speaking, an irreducible factor of this? Yes. 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 So I guess it could be other, what am I trying to say here? Yeah, it could be a bunch of things, but the right, what is it for the sixth? Like, this is the irreducible factor. Are all the other factors linear? I don't remember. Is 2-hour bus journey plus quite a bit of time wasted on getting auto rickshaw? What? Wow. Lockheed Blackbird, the lore of your life has just expanded. You've got a crazy life. And I mean that in a totally neutral way. But a 2-hour bus journey and auto rickshaw, you're an interesting person, which is good. Being a boring person is boring. So, perhaps you could write it out with roots of unity. Yeah. I just want Wikipedia to do the work for me, though. Because what about all the higher terms? We need to somehow we need to ensure that one of these quadratics, that this is, well, I guess this doesn't have to be irreducible, actually. Yeah. But it does have to be a quadratic, which, hello, Onog effects. Good morning. India is quite the place to be. Anyways, the upcoming premiere is going to be quite helpful in your group cohomology study. Yes. Yeah. Now you're going to catch up to what's happening. Good. Now I need to catch up to what's happening in my brain with this linear algebra problem that we've come back to. What are our factors here? What are the... Yeah, hang on. Let's just look this up. Factors of x to the n minus 1. Look at the Wikipedia page again. Oh, right. There we go. Yes. Okay, great. So it is just the... Right. Okay, so basically we just need to look at all of the polynomials. We could have... what? So it could factor... We could have x1 squared. We could have x minus 1 squared. We could have... No, wait. Because those don't divide anything. So it's got to be one of the quadratics. Okay, so we could have x squared plus x plus 1. We could have x squared plus 1. Good morning, Mom. Hello. I love you. Thanks for stopping by. we could have, my mom and I are twinning in the mornings because she tutors math as well. So big math vibe going on. So we have x squared plus x plus 1. We have x squared plus 1. We have x squared minus x plus 1. And then I think that's it. Although there's a big step in this proof of like, right, one would have to prove, I mean, we'd have to convince ourselves that there aren't any, there aren't any larger quadratic cyclotomics, but are you tripping or is px a bit off? You usually see the middle term be like that. Oh, it could be. Well, it's the middle term should be the. Oh, yeah. I guess it's the negative sum of the eigenvalues. I guess it's the negative sum, right? Because if it was like, if it was the diagonal matrix AB, then AB are the eigenvalues. And so the characteristic polynomial, yeah, it's minus AB. Yeah. It's probably worth writing it in that form. Okay, so okay, how does this help us though? So we've reduced to a finite list of what our possible cyclotomic polynomials are. Yeah. Although I guess actually, hang on. It could be the case, right? Because this is just the product of phi d for all divisors of n. It could be x minus 1 times x plus 1. It could also be that, I think. Maybe. So a and b are nth roots of unity, and the claim is they're actually 12th roots of unity. Would that give us the result, though? Right, because if they're 12th roots of unity, then it has to divide. Oh, right. Oh, yes. Okay, maybe we're already done. Because what are these polynomials? They're so this is like 1 and 2, and this is from 4. And x squared plus x plus 1 is the 3. And then the other one's the 6. And this is the 6th cyclotomic polynomial. So, what does that mean? That means our characteristic polynomial must be one of these. It must be one of these, and each of these divide the 12th cyclotomic polynomial. Well, each of these should divide 12 to the minus 1. Right. And then we get the result. Yay! See? See what happens when you actually pay attention to the question? Exactly what the question is asking that you're supposed to solve. Which I basically have a job, criticizing undergrads for not doing that. Funny how the world works. Okay. Well, what are we gonna do now, gang? Is it almost time? I was looking at the user's guide to spectral sequences. I was flipping through it yesterday, and I was thinking maybe it's time we get started on that saga. But I don't know. Yeah, is that a good place to start? I think so. I mean, the other place to start is a Luffy. So I kind of just want to pull it up and see. See what's going on with a Luffy's spectral sequences. Good morning, Ken. Champion of analysis. Returned to the chat, having been victorious on the field of mathematical battle. Double complexes. Spectral sequences. I should do some Serre spectral sequences. Good balance between abstract ideas and actually getting your hands dirty with them. I mean, I don't know, is that different than just starting off with like general theory of spectral sequences? Like, is Serre spectral sequences more special or something? And where would I read about those? Yeah. So I don't know. Maybe we start with a Luffy. Good morning. You think you finally understand uniform continuity? Hell yeah. We love uniform continuity over here. We love pushing limits into integral signs. Big pushing limits into integral signs enjoyer over here. Double complex. Yeah, maybe we start here. What about Weibel? Maybe. It just seems very long and dense. You know what I mean? Like, a Luffy's out here. Nice short little first pass. Like we could start with a Luffy and move our way up. The general theory is just a bit too abstract to seem motivated. If you recall, Weibel uses Serre spectral sequences. An introduction to homological algebra. Let's go. Yeah, I think the plan will be, can I please explain the direct sum? Yes. Do you mean, well, the direct sum makes sense in a bunch of different categories, but are you specifically thinking about groups or vector spaces? I mean, the answer is about the same. So let's suppose that these are abelian groups, let's say. Well, the direct sum is basically we should want to create, if we have a pair of groups, we want to create a new, a pair of abelian groups. We want to create a new abelian group. One way to do that, a process by which we see time and time again, is we form just the Cartesian product in terms of the underlying sets. Wow, that's basically it. It's just the Cartesian product. And how do we define the group law? Do I add these two things together? Well, I just use component-wise addition, right? This will be A plus C, where this is A's addition, and this will be B plus D, where this is D's addition. Now, there's actually a kind of general way of trying to determine what direct sum should be. Have I ever used LP spaces for P bigger than 1? No. Except maybe in a functional analysis course at one point. But I don't remember. What uses do locally concave spaces and quasi-norm spaces have? I couldn't tell you. Sorry, New Wave Infantry. That might even be relevant to areas of my research, but I've never looked into that stuff. There is this weird condition. A representation is called tempered if its matrix coefficients live in L2 plus epsilon for all epsilon greater than 0. Which is such a weird thing to me. But that's very different than P less than 1. So actually, yes, I mean, I've definitely proven something about LP for P less than 1 in some functional analysis course at some point, but it's been a while. But about the direct sums, so there seems to be this constant vibe in mathematics of where we have sort of two things. So let's say a direct, so union of sets, a disjoint union of sets is kind of like a direct sum, and a product of sets is kind of like a direct product. Because it turns out, for example, the direct sum, even though I wrote it here for abelian groups, just a matter of taking a Cartesian product, the direct sum and direct product are not in general the same. It turns out that for many categories that we care about, abelian groups, modules, in fact, I think a general category will have something called biproducts, in which direct sums and products are the same thing. Actually, one day I may get back to my categories of module series, where I think in the videos I put up, I might have already talked about biproducts. You can also think of direct sums as a generalization of combining the x-axis and y-axis to get a 2D plane. Wait, is that accurate? I mean, what you described there, to get a 2D plane, that makes me think about products instead of sums. I mean, a sum, I would think more about just taking the union of the x-axis and the y-axis and just having two lines instead of a 2D plane. But it turns out that these both satisfy what's called a universal property. Universal property. So what do I mean by that? Let A, so suppose A and B are sets, and let this just be the inclusion of A into the disjoint union, and let B be the inclusion and let I sub B be the inclusion into the disjoint union. So by the disjoint union, by the way, I mean I'm keeping track of each of the elements. So you could, I guess, technically also form this as a set of pairs, but now the pairs are like, you have A and then an element of A in the first component, or B and an element of B in the second component. The idea is that you want your sets, like, even if the sets had some overlap, like 1, 2, disjoint union, 2, 3, you kind of want to keep track of which, so the ordinary union, the ordinary set theoretic union, as you know, would just be the set 1, 2, 3. But what we want to do is we want to keep track of which copy of 2. So the disjoint union would be something like 1, if we call the set A. 1 coming from A, 2 coming from A, 2 coming from B, and 3 coming from B. Every point in the 2D plane is a sum of an x-coordinate and a y-coordinate. So, yeah. I mean, that's true. That's true. I mean, R2, I guess, as an abelian group, it's an abelian group, so it is the direct sum of R and R, I guess. But I mean, when I think about this, like, if I think about the set theoretic, like, if I thought about the set theoretic coproduct, then I would think about it more as like a union, as like a disjoint union. You know what I mean? The union of the axes is not the sum. Each is a copy of R. Finite products and direct products are the same. Well, what do you mean by the same? In what category are you thinking about this? So, yeah, like I said, as an abelian group, yes, those coincide, but they're definitely not the same for sets. So, yeah. Yeah, I mean, I guess what you consider most natural to think about in this analogy, I guess, depends on your tastes, right? But the point is, I make the claim now that for every set Z, and for any choice of functions f and g from A into Z and B into Z, there exists one, and there exists only one function, h, which makes this diagram commute. And what I mean by that is there's a function from A disjoint union B into Z, where h composed with IA is f, and h composed with IB is G. Yeah. And the interesting thing about that is, so maybe I should give you an example. It doesn't even really matter what the set is, right? If you have some function f that's defined on A, right? I want to build a new function from AB, right? A new function h from AB. How am I going to define such a thing? Well, h at A copy of 1. Well, I already have a function from A to B, from A to Z, right? I already have a rule for taking elements of A and turning them into elements of Z. So I will just, since this 1 comes from A, I will just plug this in, and now I get an element of Z. Okay, fantastic. And then in the same way, what is h at 2, the copy of 2 coming from here going to be? That's going to be f at 2. What is h going to be from the copy of 2 coming from B? That'll be g of 2. and h at 3, the copy of 3 coming from here will be g at 3. And so but here's sort of the punchline. So let me go quicker through some of this stuff now. So as you might be able to imagine, there is, if this is like the Cartesian product of sets, and pi a is the map that eats a pair AB and returns A, then there's also a corresponding universal property here. But now, what's the point of all this rewriting things in terms of these diagrams? Is that that's true? There is nice way for maybe one of these days I'm gonna learn more and talk more about the programming interpretations of these concepts. But the point of these things, right? Because you're like, well, why would I bother doing this? The union, right? The disjoint union and the Cartesian product are very easy to define. You can define those to, a first year undergrad, and they understand them perfectly well. Why would I bother making these more complicated diagrams? What advantage does this have? Well, the thing is, defining things in terms of satisfying these universal properties now removes the set theoretic nature of them. All it requires is that you have some objects and you have some maps going between those objects. And so what is the general context when we have such things? That is for the topic of categories. And so basically, the idea then is once we have those, we can define what it means to be a coproduct and a product in a category by just saying, well, a coproduct is some object together with a pair of maps. A coproduct of A and B is some object with a pair of maps that satisfies the universal property. For every pair of maps here, there's a unique map making the diagram commute, and then a similar thing with the arrows in the other direction for the product. And so now this gives you a hint as to, okay, how should I define if I encounter some new category, whether that is groups or topological spaces or modules or fields or a poset category or a functor category or whatever, right? Manifolds. In each of these cases, now you should say, well, I have a very general way of trying to define products, coproducts and products. What should those definitions be? Well, I'm going to go try and plug in these universal properties into that category and then see if there's something that makes this work. And so it turns out when you do that in groups, so you sort of start with this inspiration of a coproduct in the category of sets, right, which is just a disjoint union. You abstract this property, you say, let me go plunk this into other categories. And when you plunk this into, say, the category of abelian groups, out pops the direct sum. Same thing with vector spaces. You go plop this into vector spaces, out pops the direct sum. This is a cool looking image. I like the colors here and the chaoticness. R2 is the Minkowski sum of its coordinate axis, and they intersect at the origin only, so the sum is direct. Yeah. Wait, what's the Minkowski sum? In Rust, coproducts. Enums in Rust are coproducts in the category of types. Switch statements essentially define functions out of enums. I have no idea what an enum is, I'll be honest. But it sounds cool. But it sounds cool. What were we talking about before this? I just really like the look of this image right here. Am I crazy? Am I crazy? Or does that look friggin' cool right now? I think it looks pretty friggin' cool. I'd put it on a t-shirt. Yeah. Maybe I should take the, I put the banner image up. Maybe I should, because I thought it would look more interesting. But maybe for this stream, this looks like a pretty interesting picture. Like, would you click on that? I would click on that. Oh, I see. I see, Ken. Yeah. What programming language that I'm familiar with, or who Wallamran is familiar with? Lots of languages have enum types. Also Java, C++. Yeah, what is an enum type? Well, hang on a second. I also got to go back to Vibel. I'm gonna figure out where I'm gonna go. Okay, background on. Okay, let me put this here. Enum types. No, not types. Well, enum types. Maybe TypeScript should be there. I know nothing. Spectral sequences. Spectral sequences 120. Let's go look. Ooh, we gotta go further. Nice. I mean, I guess a lot of these books are built the same, right? Is there a big difference if we use this versus a Luffy? I guess actually, you know what? This is maybe more close to the terminology people actually use. Giga Chad Luray moment. Oh, an enum is an enumerator. Oh, okay. That already helps me understand things a little more. Yeah, I mean, is there a big difference between using Vibel here or the user's guide? Yeah, I'm not sure there's a big difference. Oh, and this jumps right into, this seems to jump right into some applications. Enum is really just a type that can have some specified set of named values. Interesting. And C and C++ are encoded as integers. Well, in other languages, they're probably their own thing. Okay, I gotta go over to the other tab and check that out soon. Actually, no, Vibel looks pretty cool too. I don't know. I think I might start with user's guide and then I'll come here. But this looks good for examples. Tough to say. I mean, this book also does seem to jump right into group cohomology in the chapter after. Hypercohomology. Yeah. Enum type, enumerated type. Let's see what Wikipedia has to say. I bet NLab's like an enumerated type is infinity morphism between infinity categories of the type of all programming languages or something. In computer programming, an enumerated type. Oh, it exists in the R programming language? Interesting. Is a data type consisting of a set of named values. Okay. Enumerator names are usually identifiers. They behave as constants in the language. An enumerated type can be seen as a degenerate tagged union. Okay, that makes sense. Of a unit type. I don't even know what a unit type is. A variable that has been declared as having an enumerated type can be assigned any of the enumerators as a value. A variable that's been declared as having enumerated type can be assigned. Okay. What's going on in chat? STD variant? I don't want any variants of any STDs. Thank you very much. Have I ever come across or used hyperreal numbers ever? I've certainly come across hyperreal numbers. Have I ever gone any deeper into them by just looking them up? No, not really. Have I used them? No, I wouldn't say. What can be done with hyperreal numbers? Hyperreal numbers. Hyperreal numbers. Yeah. I don't know. I think it's just a way to try and one of these attempts to make infinitesimal calculus work. I mean, I've worked with dual numbers in some sense. But yeah. Crash course in Rust may be a bit too much to type here. Try to just apply the definition of coproducts you just learned to the category of types and functions between types as morphisms. Unit type is terminal object in the category of types. Okay. I mean, then yeah, okay. You can either define epsilon to square to 0, or you can do it without making it a zero divisor. Wait, really? You can do it without making epsilon a zero divisor? Right, I recall the hyperreals being a field. Yeah, something about these ultra powers, ultra filters. I remember in my undergrad, one of my good buddies in undergrad, he got really interested in this, I think, and started studying like ultra filters and trying to understand them. I remember him telling me about some of this back in the day, but yeah, I don't remember. We should have some learning Haskell streams here in preparation for the learning lean live streams. Is that necessary? I don't think that's necessary. Tomorrow we start spectral sequences, I think. And then maybe lean. I mean, definitely if I get this job in Sweden, we'll definitely be doing lean learning and automorphic forms learning. For sure. Hot take, hyperreal numbers is a subfield of recreational math. Maybe. What is recreational math? What isn't recreational math? I've seen some papers. I've seen some papers in published journals that I would consider like beneath recreational math, and I've seen some recreational math that has some very deep ideas in it. So, recreational math is If you think something's recreational math, then it is. Yeah. You constantly work with hyperreals, but only subset. Yeah. It's how automatic differentiation is implemented. That is interesting. Hyperreals are apparently the largest ordered field. What? What does that mean? In the sense that all ordered fields are isomorphic to a subfield of the hyperreals? What? That's cool. That's crazy. Or was that surreals? Okay, yeah, I don't know. I always got the two confused. Both weirdos. It could be fun to do some learning on that sometime. Yeah. Like, I'm sure the people doing like the fanciest versions of Langlands these days look at my paper as recreational. My preprint is recreational. And then there's other people who probably look at it and they're like, what the hell is this? There's a crazy shit going on. So I don't know. Definitely don't need Haskell before Lean, but they're the same family of languages. I see. You can do serious algebraic geometry with hyperreals, not just recreationally. Well, I mean, yeah. I mean, in the sense, yeah. So that's why I said, I mean, I've worked with dual numbers. Like, you can use the dual numbers to like define like algebraic tangent spaces, and then you can use like, I think in like Getz and Hahn's book they show how to recover the Lie algebra of an algebraic group, but you do this functor of points perspective, and so you're like taking Homs into the dual numbers over your field or something, and yeah, you get out the Lie algebra. Yeah. If I get time, I gotta watch a talk. Kevin Buzzard, Capturing Mathematical Equality. I don't know if I've seen that one. Oh, I've definitely read his. Big Angela Collier fan over here, by the way. Definitely one of the best physics YouTubers to do it. Why? What am I? Buzzard. I definitely read. What was I going to say? His archive thing on equality. So, let me see this. Capturing mathematical. From a year ago. Yeah, I don't know if I've seen this one yet. But I have definitely read his what is it? Kevin Buzzard. Also, I've interviewed him on this channel, by the way. If you didn't know, go watch my interview right after this with him. Kevin Buzzard on equality. He's got this little note on archive. Growth and Deek's use of equality. This is really good. I suspect he's just going to say the same things he says in that paper. But you should definitely go read this. This is one of the great little note, I think. Yeah. It's true. He is an FLT he is arguably the FLT formalization guy. But before that he did work in algebraic number theory and the Langlands program, and he did a lot of respectable work in pure mathematics. And now he still does respectable work, but since 2017 it's been in the world of proof assistance. So yeah. Anywho, I think on that note we're gonna end things here. So yeah, I think tomorrow we start with spectral sequences. So get ready. Get ready.